Reaction mechanisms is the subject of this video, and this is a topic that comes up not in first-year chemistry, but in AP. Typically, when we think about reactions that we study in introductory chemistry, most often we think of forming a precipitate, maybe a reaction that occurs in aqueous solutions. And a lot of times with ionic compounds, the reaction does happen in one step. However, the subject of this video and the slides that follow discuss reactions where actually we have covalent bonds being broken and new covalent bonds forming. And this doesn't all happen in one step. So that's the subject of mechanisms. If we look at a balanced equation, it doesn't really tell us how the reactants turn into the products. And that's what a mechanism is all about. Looking at the reaction of nitrogen dioxide with carbon monoxide, you see here two different steps in the mechanism represented on a molecular level. So we have a nitrogen dioxide reacts with a second nitrogen dioxide, forming NO3 and NO, followed by the nitrogen trioxide. And remember, this is not the nitrate ion. These are molecules, a little different than what you're used to, combining with carbon monoxide to form NO2 and CO2. These are the two steps that have been proposed for this particular reaction. If you add up these two steps and cancel the like terms, you come up with what is called the overall reaction. NO3 is called the intermediate. Do you have any idea why that is? Upon inspection of the two steps, you can see that the nitrogen trioxide is first formed and then later consumed in the reaction and doesn't appear in the overall equation. Here's a different reaction. The rate law is expressed below, so you can tell from the rate law that it is first order with regard to NO2 and first order with regard to F2. Remember, the rate law doesn't necessarily agree with the coefficients in the balanced overall equation. First step in a proposed mechanism, first and second steps are shown below, with the first step being the slowest step in the mechanism. Do you agree with the identification as F as the intermediate? In a mechanism, the steps are called, as it says, elementary steps, and the rate of each reaction refers to its molecularity. So when you have, as in the previous slide, two reactants combining, this would be called a bimolecular reaction. Second step, also a bimolecular reaction. If there's only one molecule, it would be a unimolecular, and that reaction is first order. So it turns out the steps in a mechanism, the coefficients can be used to determine the order. But in an overall equation, you cannot use the exponent. So you have to look at the information given in the problem and decide, is this the overall reaction or is what you're given steps in a mechanism? So you can see that this last example here would be called a ternary reaction where three different molecules, actually the last three different substances need to collide in order to produce the products. If you think about it, what are the odds that this will happen? Slim. These last three examples of mechanistic steps are very unlikely. So when you have the slowest step in a mechanism that includes an intermediate, it's important that the intermediate is not shown in the rate law. And so we have to use stoichiometry to help us get rid of the concentration of this intermediate. So the next two slides will show us that process. So if you look at this reaction here, this is the overall reaction. And so for this example, a proposed mechanism is found below. And what we want to do is look at the experimentally determined rate law to decide if the proposed mechanism works for what was determined to be the rate law. If we can do that, then we can say, well, this is a possible mechanism. It doesn't necessarily prove that this is the correct mechanism, but at least it shows a possibility. So, since the second step is the rate determining step, first of all, we can say that the molecularity is 2 because it takes 2 molecules coming together to produce the products. We can write the rate law for the slowest step, but notice that the rate law includes the reactant N2O2, which is not part of the overall equation. It is then called an intermediate. There's a little bit of detail right here, but if you just simply look at the mole ratio in the previous equation between the intermediate N2O2 and NO, you'll see that the ratio is 1 N2O2 for every 2 NO. And so if you substitute in to the rate equation that we wrote that included the intermediate 2 NOs, you will end up with a rate law in yellow here. The rate equals the constant times the concentration of NO2, the 2 coming from the coefficient in the previous equation to eliminate the intermediate, times the concentration of oxygen. It's a times here. There's not a addition sign. So one more example here. We have the overall reaction. We have the experimentally determined rate law. We have possible mechanisms. Again, here in this example, the slowest step, you have to look, there are 3 of them in this case, and the second one is the slowest step. The slowest step could occur in any of the 3 reactions. It just depends. How these are determined is beyond the scope of this class, but in more advanced classes, you'd be able to study this. So since the second step is the slowest step, and since the molecularity is 2 molecules coming together, the rate law is expressed as rate equals the K times the concentration of IBR times the concentration of BR. However, if you look at the overall reaction, you can see that BR isn't the intermediate. So what we have to do is look at the equation above, seeing that the mole ratio between BR and IBR is 1 to 1, we can substitute into the rate law for BR, we can substitute in IBR and come up with the overall rate law. So in summary, a proposed mechanism can coincide with the experimentally determined rate law. This shows that the proposed mechanism is one possible one, but it doesn't mean that it's the correct mechanism. Much more advanced studies would need to be done, and that is, again, beyond the scope of the class. So, the next stage of discussion of kinetics involves collision theory and activation energy. And as you've studied in lab, the concentration changes affect the rate of the reaction, as does the temperature. And what's important is not only the number of collisions, but the energy and orientation in which they collide. 2 terms to remember are activation energy and what's called the activated complex. Sometimes it's referred to the transition state. That's sort of like not a molecular substance, but a transition where some bonds are being broken and other bonds are being formed. And if we want to show a graphical relationship of this reaction, we can identify the activation energy by the height of the hill that the reactants have to climb. Notice that the line goes to the top of the hill down to the potential energy of the reactants. If I wanted to look at the activation energy of the reverse reaction, however, the line of the activation energy would start from the products and go all the way to the top. So the reverse reaction has a higher activation energy, as you can tell. Definition: activated complex is that intermediate step in energy. It's obviously higher in energy, as you can tell by the graph, and this is not an isolatable substance. Another feature of a graph, this is a little skewed, the difference in energy between the reactants and products is the delta H for the reaction. You hopefully recognize this as an exothermic reaction. For this reaction, the one where bromine, nitrogen, and oxygen are bonded together, and two of them react to produce 2 molecules of NO and 1 molecule of Br2, the transition state is, as shown here, the activated complex, where the bond between two bromines is being formed, and the bonds between both bromine and nitrogen and the two different molecules are being broken. So, a little bit of information about how we calculate the activation energy and the relationship. It's related to temperature, and as the temperature of the molecules increases, then the molecules not only possess more energy, but then their collisions are more effective. And this increase in temperature brings about an exponential increase in the reaction rate. A little bit complicated, but I'll just show you the equation in case you're interested. The number of collisions that is required for reactions to occur is represented by this equation, where E sub A is the activation energy, and some of the other constants are familiar to you. And so, I'll zip through this slide. I think it's more concrete to look at this one. So if you look at the orientation of these two molecules, you can see the reaction that does occur. Again, another molecular representation of the reaction. If the molecules are not oriented properly, then no reaction would occur. So this is more of a statistical analysis. I'm not sure if anyone in the class is in statistics at this time. But if we do a little mathematical manipulation of the Arrhenius equation, we have, in the end, one that looks like this one here, where K, just ignore this part, is equal to A, a constant, times e to the minus E sub A over RT. This will be very valuable for you when you analyze your results from lab. And again, further manipulation, taking the natural log of both sides, will give you this equation. Now we've got an equation for a line. This is where you're going to find your E sub A, because you're going to be plotting the natural log of the rate constant by the inverse of T. And that will give you a line. If your T is in Kelvin and you calculate the slope of your line by graphical analysis, you'll be able to find your activation energy. Another way of finding slope, change in Y over change in X. As you can see here, that's precisely what was done to find the slope. Second example, finding the slope. All right, in conclusion, we have the activation energy is related to the rate constant. The slowest step is the rate determining step, and it has the highest activation energy. A graphical relationship of this is shown here. First step, second step, third step. Looks like the third step is the quickest, but what's most important is the rate determining step, which is the slowest step, the one with the largest activation energy. This points out the location of the intermediates. Those are isolatable as opposed to the activated complex. Those structures are not able to be isolated because they are bonds that are part formed, part broken. And finally, catalyst. To understand how the catalyst works, there are a number of different types of catalysts, and that's where we're going to wrap it up here. We've got catalysts that are used in cars as catalytic converters. We have enzymes in the body, many different types of catalysts, broken down into basically two categories. Homogeneous, your lab would be a homogeneous catalyst, and a heterogeneous catalyst. For example, your catalytic converter in the car or an enzyme might be examples of heterogeneous catalysts. So the mechanism is different with a catalyst. It lowers the activation energy, and since more molecules will be able to have enough energy to cross this activation energy barrier, the reaction will go faster. It does not change the delta E or delta H as you know it at this point in time. Graphical relationship of a catalyzed versus an uncatalyzed reaction. Here's another graph that's important to understand, that if the activation energy is decreased, notice that the horizontal axis, the activation energy is shown here. If the activation energy is decreased in a catalyzed reaction, then the area under the curve, which are the number of molecules that have greater than the activation energy, then the greater number of molecules will have sufficient energy to react. An example of a catalyst similar to what is in your car, although hydrogen isn't what's broken down on the surface of a car, but this is how hydrogen bonds are broken on a platinum catalyst. Partially hydrogenated vegetable oils the process is done this way. You have saturated hydrocarbons, has multiple bonds, and you have hydrogens that are on the surface of a catalyst, and these hydrogens are going to be added across the double bond, taking the double bond into a single bond. That's how unsaturated fats, this is an unsaturated fat, not a saturated fat. How unsaturated fats, commonly referred to as the healthy ones, are converted into saturated fats, sometimes known to be the unhealthy fats in molecules. This isn't really a fat, it's a small hydrocarbon, but fats are just longer molecules with multiple bonds in them. So, as you can tell, there's 4 steps: the absorption of the reactants under the catalyst, the molecules that are going to react moving close to each other, the reaction that occurs, and then the products leaving the surface of the catalyst. The catalyst is then free to react again and again and again. If you think about it, if you have contacts and you use this hydrogen peroxide solution, the catalyst is that gray disc at the bottom of a contact case that is often used. Chlorofluorocarbons have been eliminated from propellants for close to 30 years now, I believe, but their presence in the upper atmosphere are still responsible for part of the depletion of the ozone. Enzymes, they're viewed as a homogeneous catalyst. I stand corrected. An interesting thing that comes about is that eventually a catalyst can speed up a reaction, but to a certain point. Perhaps you saw that in your lab. I'm not sure yet, since we did an experiment differently this year. as you can see by the graph, eventually the rate of the reaction levels off and doesn't depend on the concentration of the catalyst. Hope this podcast has been helpful. Have a good day.